So, good afternoon. This is a special day. My train was delayed only by 5 minutes, so I arrived in time. And we have some stuff to discuss. First of all, not my directory. So this is the day, and this is it. I promised you to ask you when do you want to take and pass the exam. The problem is that they asked me to provide the dates, time and everything in short notice. Actually, the deadline was 28th of October, and I got the email on 30th of October. So after 2 days of the deadline, so I could not ask you. Many of you, or some of you, asked me to give opportunity for the exam in December. Then you can pass, and then you don't need to come back after Christmas. Well, we will see. So the times, December, it's Tuesday, the first Tuesday of the examination period, and then in January, every Monday. This is the best that I could give you, and we have to discuss some other things. The exam will be written exam. I don't know where it will be. I asked a room, a hall for 40 persons from 2 until 4 on the time of the exam. At the exam, I will ask, theoretical questions. Honestly, so there is the physics. You can read the Fermi. The Fermi is a tale comparing the number of Lipschitz areas that I learned, and my deductions are not very serious. So I will ask you on the minimal formula, and I will ask theoretical questions. Short, terms, definitions, and I will ask you to describe processes. How the conductivity works. What is the difference between the special and general relativity theory? What is a Galilei and what is a Lorentz transformation? So there will be short questions, longer questions, and I cannot ask you to write exactly the same that I told you. So you write with your words what you have understood. That's the written exam. The written exam, you will get a grade for it, and you mustn't use anything. I got freehand about tests and grades. So my proposition, I propose that to write the midterm exam on 1st of December, and the retake of the exam 18th of December here, and in the time of this lecture. I think that's the simplest for all of us. There is a typo, that's December 7th. It should be 15th of December, 14th of December. Until then, you must have the signatures and the grades. However, if it's not possible to get the signature, you can come from December 16, which is after the deadline, but I not really understand, but the secretary explained some administration. Perhaps it's like good that there is no automatic system without contradictions. Never mind. So you can come right and everything. Now today, the theoretical part will be quite short. We can do more practice and exercises. So I can give you today or this week the next homework. And after the next week, I will give you the third one. I have no clue when I will give you the fourth and fifth one, but you will get that. Don't worry. And I have to figure out what to ask from this very theoretical part. Okay? Is it okay to write the test 1st of December and take not tests, midterm exam? That's the form, but I call test because the Hungarian exam is a test. Is it okay? 1st of December? And the 8th, if there is any bad, then you can take it on YouTube. Yes, and for the exercises, the test, the midterm test, you can do anything that you want. The only thing what I will ask you to put your communication stuff in front of you or further. So do not communicate to each other. But you can use your notes. You can use anything. Why? Not because I'm so kind. Because I don't ask you in tests to memorize the formula of the de Broglie wave, for example, wavelength. What I want to see that your brain is working, you understand the processes, the methods, and you can solve problems, fix problems. Because this is that you will need in your time. Don't worry, if you do something a few times, 100 times or something else, you will know everything by heart. So, but it's not necessary to know all formula and everything for the different tests. I don't know whether it will work. It worked in other time. Just do not mix the two things. The test, you can do anything except communication systems with each other, but the exam you cannot use anything. Okay? Okay. Then we have 3 lectures today, next time. Then there will be the autumn holiday. I don't know why. Do you know that in Hungary, last week had the autumn holiday in primary school, secondary school, and any other universities. My former wife was happy because she could not give me the kids for half of this period. But here it starts 17th of November and ends 21st of November, the autumn holiday. And then there will be one final lecture and practice on 24th of November. Test or midterm exam, whatever you want, retake of the midterm exam. And then the situation is that it's enough. We will be able to do anything. So, last time I talked about the band theory, metallic bonding, electrical conduction in metals, and other things. Here there is a mistake. I will not talk today about thermoelectric phenomena, but I will talk about the other stuff next time and a lot of other things. I think these are exciting modern physics and very practical. I think it's useful if you know how the liquid crystal is working, what is superconductivity, and other things. I think it's good. I hope you agree. If not, well, it's up to you. Okay, so now I will talk about the transistors and semiconductors. I have told you a few sentences last time at the beginning of the lecture. So we have this periodic system of elements. There is a very, very special element, this silicium. No problem. So this silicium is really, really distant. It's very common at the Earth. You know, the universe actually not all planets look like us. Usually they consist of mostly hydrogen and helium, some methane, ammonia, ammonium, whatever. For example, Jupiter, Saturn, Uranus, and the Neptune looks like this. But we are, so this Earth, Venus, Mercury, Mars, made from rocks. The main ingredient of these rocks is silicium dioxide. Silicium is below the carbon, so it has four atoms, four chemically active atoms. It's very similar. You know that the carbon, I hope you know, I think you know because, well, I don't know what the Hungarian students know, but in my time I learned that how the carbon looks like. There is an amorph version, it's just cool, we eat with it. There's the graphite, it has a two-dimensional structure and you can write it or draw it or you can use it as electrodes because parallelly the layers it conducts the electricity. It has a special reason. Actually, you can guess what is the reason. And the nicest part is the diamonds. When all carbon atoms has covalent bond with the neighbors. It's crystal, it's beautiful, and it's really perfect, and it's very high. The sixth and also you know that the carbon is one of the main ingredients of life. And now we have the silicium. The silicium has many common features with carbon. For example, perhaps I told you, you know the Frank Herbert's Dune. There are 3 different movies made from this, and the childhood has a special metabolism based on not carbon but silicium, and what they breathe is not oxygen, it's sulfur. So the silicium is sometimes very, very similar to the carbon. At least with the 4 covalent bonds, chemical bonds, the neighbors. It's very, very common. If you go to the shore of Danube, not here in Budapest, but for example, if you come to my place, do you know where is Koch? There is a nuclear power plant in the middle of the country, but there is another interesting stuff. The Danube rose little stones until Koch. Then all islands and everything that we built is made from sand. And the main ingredient of this Danube white sand is silicium dioxide. So you have to take the sand, you have to clean it, and then you have silicium dioxide. You have this silicium dioxide, I don't know how, because I'm not an engineer, not chemical engineer, but you can remove the oxygen and you have silicium. The silicium is not metal, is not really non-metal like carbon. It's between them, it's semiconductive. Because last time I explained you, there are electron levels that are allowed, and there is a bind zone, a forbidden zone between them. And this forbidden zone is very narrow in silicium. 30 years, I would have developed some chip factory and microelectronics in Hungary. I told you actually how it works. You know nothing, just sand and some import material. I will tell you which material are there. And many knowledge and lot of work to do these chips and microelectronics. If you don't have so much knowledge, doesn't matter, I told you, doesn't matter. Which is important is silicium. We have the silicium. The silicium has this electron configuration. The main, in the middle, the first principal quantum number is 1. There are 2 electrons. Then the second layer, on the second layer could be 8 electrons. It's also full. But then you have 4 electrons. And it has special importance. The germanium is very, very similar to silicium, but if I remember well, it's liquid at 30 degrees or something like this. It's very expensive, actually. It's not as common as silicium. Do you know why? Why is the silicium is very, very common, and also the iron is very, very common, but germanium and gold and silver not.
Because
yes?
silicon has a longer half-life time, so it's more stable.
This is a good answer, but it's just part of the answer. Do you know how the chemical elements are made? Were made?
They form bonds with the elements.
I mean not the elements, the nucleus, the atoms. Yes?
Inside of the hearts of stars.
Yes, yes. And what about stars and the knock fusion? I mean the nuclear fusion.
With less heat and pressure, they create even heavier and heavier elements until they burn at potential.
Yes. So the last element that is so the fusion must produce energy, and also the fission must must produce energy, and until the iron it produces energy. Iron and nickel. Nickel perhaps is not being sure. And Ni, so that's the stuff. Then the stars collapse, and during the collapsion, you can the process made gold, polonium, uranium, platinum. So all of us, I mean the atoms of our body, was in the middle, in the heart of dying star. Otherwise, we would consist only hydrogen and helium, because 99% or more of the universe is still hydrogen and helium. 75% of the material of the universe is hydrogen. Almost 45% of the universe is helium. The reason is the Big Bang. After the Big Bang, these elements was made. The first stars were only pure hydrogen, helium, lithium, deuterium, and that's it. There were no metals or anything, and they last longer than the second generation of stars. Some of them still exist because the small stars live billion years. The big giants live shorter, only 10 million years. The sun is a yellow dwarf, so its lifetime is 10 10 billion years. It's different. Okay, so this is how these elements are made, and these elements are also will be important because they help the silicium to conduct electricity. Important. To mine electrons and everything that I say, you need pure silicium. It is polluted, and the crystal structure has error. Then it makes problems. You will see why. But the silicium crystal must be perfect and pure. It's very, very difficult to do this silicium. You need knowledge and you need energy, but you don't need so many materials, just silicium. And also you have to do the perfect crystals. I don't know how they do, but it's an interesting topic, I think. Okay? Sorry for the Hungarian text. It's quite time consuming to change them. If you check the Moodle and the GitHub, then the final version, there are no Hungarian text. So the first on the left is, it says this is the covalent chemical bonding in the silicium crystal. The other is the structure of the silicium crystal. You have one silicium atom, and it has one, and one bond connection to the neighbors. It should be quite pure. It should be not quite. It must be pure, and it must be perfect. Okay, so this will be quite interesting, and sorry for the German text. And sorry for this also. Okay, you have perfect crystal, but here there are. Okay, it's that's why you learn quantum mechanics, because in classical thinking you cannot understand this. So there are waves of electrons there. There are levels that are allowed because the electrons could have only certain energies, and so there are more electrons, so there is a band, so it's not only just a line, it's a band, and there is another band. And the difference, the gap, the forbidden region between the two conductive layer or layer is narrow, it's stuck. So what it means? It means that if you have some high energy electron, for example, you heat the material, the silicium, then you have conductivity. It's weird because usually when you heat something, then the conductivity decreases. So if you switch on a hot toaster, sometimes it switch off the electricity because it's too cold. Then you have a washing machine and a computer and also the baker and everything. But it happens a few times. So here the situation is different. Also there is something very interesting. This electron that starts moving, this electron moving, that's fine. But from where it's missing, there is a hole. And this hole is because there is a balance and neutrality in the crystal, is a positive hole. So you have negative and positive electron is understandable, it's particle. But its missing place is a positive hole. It also helps in conductivity and it also moves. Okay. Yes, okay, this is what I told you, actually. What I have told you, this is, sorry again for this Hungarian text, it means electron energy. Then UCOP means holes, and conductive electrons, that's on the top. This is the same that I told you with energy, with the band theory. You have some electrons, there is a what is it, excitation. They are excited, and they jump from one layer to the other. And when they are in the valence or conductivity layer, then they are moving. But on the bottom, there are holes, and they are missing. That's an interesting feature of semiconductors. Okay, that was, this one was the case when you have pure, clean silicium crystal. The crystal is perfect, well, they exactly perfect, but you can reach it, and there is no pollution. The pollution would help. Okay. On the bottom, you can see boron, silicium, and phosphor. It's quite close to the silicium. Actually, it's very, very interesting. The bore and the phosphor are not metals. So the aluminum is more common than boron. And but you cannot use this purpose because it's a metal. Phosphor also not a metal, so they are not conductive. You know the feature of phosphor, don't you? For example, it's good for lightning bullets or burn full cities and so on. The bore can actually what is the name? Not emit. Absorb neutrons, for example. In the nuclear reactors, when there is a big problem, then they try to put hafnium or boron columns in the core. But if nothing helps, then they flood it with water and boron. Doesn't matter. So boron has 3 electrons. The phosphor has 5 electrons. Silicium has 4. Let's go back. And now we put first on the left a bore. The bore feels perfectly in the crystal of silicium, but it has only 3 electrons. One is missing. That's a positive hole. Not like in the pure one, it's a different case. There is a different stuff. The other, this blue, is phosphor. The phosphor has 5 electrons, so phosphor is perfectly fine in the crystal with 4 electrons, and it has a plus an extra electron. It's an hole, it is also a hole, and a negative hole. So we have a positive hole and a negative hole. With this, you can build up transistors actually, but you should understand what is going here right now. This is how it looks like. Yes, it's yeah. The text is the same that I told you. Okay, this is the N on negative type doping and donor levels. You put the phosphor, and the phosphor's energy level is lower than the valence band of this lithium, so it helps to conduct. There is another case. You have p-type or positive holes, and it looks like there are some energy levels that are higher than the lower band. So it's easy to jump from one place to the other. Okay, I told you this. The problem is that it's not perfect. Explanation. Oops. There is no. That's funny. There is no internet. That's a problem. Serious? Yes, I'm a bit senile, so. I guess you know this, or if not, then are very young. In the old days, before my time, when my mother was young, my grandmothers and grandfathers were young, they used diodes in electric transistors and diodes in electric currents and facilities and radars and everything. It is very simple, you know very well. It allows to flow the currency only one direction. So if you have this you can see, so if you have this P-polluted silicium, and if you have this N-polluted silicium, and you put them together, you got a diode. It looks like exactly the same. But the big difference is that the original made from glass and metals is the size of this mouse, and the minimal size is like my finger. But the minimal size of this could be nanometer, a few nanometers. This is called electronic revolution. This happened in the 70s and 80s. This led us to the computers and the world where we live right now. When they landed on the moon, they used classic computers, and one cell phone now has higher capacity, calculation capacity and memory than the shuttles had. And also it was very challenging to calculate the orbits and everything, because in that time the computers look like a full room. Actually, this is in my lifetime, when I was something 10 years old, then I visited a computer where they made a forecast for the water level of the Danube in my city, and they showed me a computer brand name Ural, you know, it's a very familiar name, and it was one room, I mean whole, the size was like this. And in that time, debug meant that you took the smallest technician and asked them to take the bug from the electricity currents. But this one is much more effective. If you do this, if you put together more, then you also here. Yes, this is it. Actually, perhaps in the final slides I will put them. This, what you can see, you have positive holes here, negative holes here. They attract. One moment. They attract each other. And if you have current from this to this direction, then it flows. That's okay. If you have the opposite, you put electricity in the opposite direction, then these positive and negative holes will separate it, and they shut down the current, the way. So it will not work. It looks like a diode. It works like a diode. Just it could be 10 nanometers or something like this. It's okay? So this is why you learn this, to understand this, how the microelectronics work. And then there are processes how you can do it. I don't know how they refine the silicium, but what I can recall, there are these, not samples, these, so they, photonic, so they made the full currents and electricity and everything with visible and ultraviolet light, and they made like an image, and then they with acid remove one layer. Then also they made not photos, so somehow it's like some photonic stuff. They put the next layer, and then somehow they put together this microchips. But it's very far from my field. That's your field. You will know this by the time you will leave this place, I guess. Okay, I have diode. That's fine. Yes. Yeah. the photodiode has something extinction and everything, but I didn't check what is it. What I would like to show you that's it. Do you know what is it? It has 3 legs and black. The piano is a wrong answer, so here you must answer it's transistor. This is how the microchip looks like. If you have an N polluted, P polluted, and M polluted layer, there is one electrode here. Oops. One electrode here, and there is a third one. And you can do you can allow the with the with some potential, you can allow to flow or not flow the current. It's a transistor. This is missing from the slides. I will give you some example. I will actually save them right now, and then there will be no problem with it to find again. Oh, what's this? I know. Okay. Have you learned about this in microelectronics or electronics or anywhere? Because that's a faculty of engineering, electrical engineering. So perhaps that's just a repeat or that you already know. Have you made this before? No? Yes? Undetermined? Okay. No answer. You are shy. Okay. Where we are? Here. Okay. I will add these slides with some text to the lecture slides. I should have done it yesterday, but well, doesn't matter. Because that's important. Okay. Some other important things. If you do not understand this, that follows, then the problem is not with you. When I learned from the non-knowledge series. There were theoretical dynamics, statistical physics, quantum mechanics, electrodynamics, a lot of things. And then on my third year, that was preparation for specialization. Now it's called MSc. We learn quantum statistic physics. This Fermi-Diract statistics belong to them. You have seen only a few parts of quantum mechanics, so that's quite challenging to understand what is going here. The electrons are not alone in the metal. However, this is more general, not only electrons. Everything which which has half spin, or not really half, 1.5, half, 2.5, because there are more particles, we call them fermion, named by Enrico Fermi, which has a spin 1, 2, 3. So it's, then we call them bosons. We don't deal with bosons here, but they are very, very interesting. Whereas at superconductivity we will deal with it. But now the fermions are interesting. There are 4 quantum numbers: principal quantum number, orbital quantum number, monetary quantum number, and spin quantum number. The Pauli principle says on one orbit could be only one particle with the same 4 quantum number. So, for example, for spin should be something different if you check. And this is true not only for the atoms and molecules, but also in metals, in cloud mass of atoms. So, in the metal, you have an electron gas. It's called Fermi gas. It has a very serious importance. It's very, very serious. It's very, very important. You have energy levels and different levels, and you put the particles in them, the electrons. Actually, you do not put their R in the metal. And they start to fill the lanes. And there would be limited number of particles in one layer. So it's not like like macroscopic particles that you can put whatever you want. So they are on special levels. And they have special collective behavior, actually. Yes, half integer spin particles. Great. Okay, this is what I told you. You have large number, yes, fermions, half spin particles. For example, protons. Protons also have a half spin. Okay, so you have many particles, electrons. These electrons are nuclear, and then you start to build the Fermi-Diract statistic. You cannot distinguish the particles; they are the same. I mean, they look like the same. Energy levels are quantized. I explained the Pauli exclusion principle, and the 4th one you learned because I explained you. No, it was not me. It was before me. It was me. I explained you this uncertainty relation, Heisenberg uncertainty relation. You cannot determine exactly the location and the impulse of a particle. There are some uncertainty. That's the Heisenberg uncertainty relation. So this P, I mean delta P, that's uncertainty, and delta X defines fast space volume. Do you know what is fast space? You must know reference system. In reference system, you have coordinates. But if you want to give a macroscopic what is state, then you have to give the velocity. It's much more convenient if you give the impulse, its velocity times mass, and then you have something that is consists of coordinates and impulses. And in theoretical mechanics, that is called Lagrange mechanics and everything that you will not learn, but it seems to be sometimes it's important. You give the status, the state of a system with giving the coordinates and the impulses. So that's absolutely not simple. I will show you a monster. The monster's name is Brassiator. It's a very, very special code. It consists of millions of euros to develop it, and you need hundreds of thousands euros to run it. It's a plasma simulation code, and I hope that I will find something suitable example. No, not really. Okay, this is not good. It's better, much better. Oh yes, just I have no access. Just a moment, please. No, it's better. It's open source. No open source. Still not. Better. It's here. No, it's something different. Okay, I will not show you, but so this coordinate system of location and impulse is quite common to describe the status of a system. Okay. The Fermi-Diract statistic is a probability density function. Okay? Does it tell you anything? Have you learned probability theory? You, yes. And the others? You have learned probability theory. So this gives that there is a case, and how many percent and how many case could be in. So you have two cubes, and you throw them. So the possible result would be, I I mean the sum of the values. Or yeah. So this could be the results. There could be 2 only once. 3 1 2 2 4 1 2 3 5 1 2 3 4 9 6 1 2 3 4 5 7 1 2 3 4 5 6 8 1 2 3 4 5 6 9 1 2 3 4 5 6 6, okay, again. Yes. Okay. 10 1 2 3 4 5 6 okay. 11 1 2 3 4 5 6 Something is not good. And this is 5. Something is not good. Sorry, I made some very mistake. Oh. Oh, yes. Yes, yes. So, 1, 2, 3, 4, 5. Oh. Oh, that's okay. Aha. Aha. This is bullshit. And now, until 7, that's fine. 8. Okay, that's better. Okay, and then you have the cases Okay, so I don't know why I did this, but at least this is a probability function. You have two cubes, you throw them, the result could be from 1 to 6, and this is the sum of this. And this is the cases and how many cases, how many percent you could have. So these are describe such a function, the probability of how many probability of the different cases. This is here describe how many particles are on different levels. It has no units. It's a number. It's probability. And what is here? You have the temperature, the Boltzmann constant. You have an undetermined Fermi energy. I will explain to you later. and you have this energy. And this is the explanation. You are sitting people in the theater, and they are sitting here, here, and you will got a number of the people on different row. The one row is one lane, one energy lane. If you plot this, you will get this function, probability as the function of energy, and there are some special part like Fermi energy. Yes, so this is the Fermi function, and this Fermi function gives the probability that an energy level is occupied by an electron. There are special cases at zero absolute temperature that you never reach, and other special stuff. I have to find exercise for this. Not now, for within a few weeks. This is the same. So this function describes the probability of that there is a particle in a certain particle level. And also you can calculate density distribution, density function for this. Okay, we have this one. So, no one understand, we can continue, carry on. We had exercise about the photoelectric effect. You have quantum arrives and it gives an electron, and the electron leaves the metal. This is the explanation of it. You have, sorry for the Hungarian text. You have the metal, and the metal bounds the electron. And this bound can be calculated with this Fermi function, Fermi-Diract statistic and everything. And how much energy is necessary to hit the electron and to remove the electron? That also can be calculated. Yes. Okay, and usually I give it to you. That's I don't know. It's 2 electrovolts or something like this. This Fermi energy also gives some quantitative result for this lanes, that those lanes are full of and allowed to occupy by electrons, and which lanes are forbidden. And that's it for now. Now we have a short break. 10 minutes, and then I will continue with we will continue with the practice. Okay?